Well, Aymeric, why don't we just we'll just go ahead and get started. You know, people tend to trickle in a little late sometimes, but um, that's fine. Let me
Yes,
just make a
sure.
couple announcements first, and then I'll hand it
Yes.
over to you. Welcome everybody to the Planetary Fluid Dynamics Seminar Series. I'll just put some email in the chat for you. If you want to get the reminders to come, you can just send me your email. Next week, not next week, next time in 2 weeks, on the 26th, we have Dan Chavez from Purdue University talking about tropical cyclones on Earth-like planets. And today we have Aymeric Spiga speaking. Aymeric got his PhD from 2008, in 2008 from the University Pierre and Marie Curie. And since 2010, he's been there and also at the Laboratoire de Météorologie Dynamique in Paris, where he's been a lecturer for since how long have you been a lecturer there, Aymeric?
Since 2010, yeah.
Since 2010, yeah, great. And today he's talking to us about studying the atmospheric dynamics of giant planets with global climate models. So why don't you take it away?
Yeah, thank you very much, Jonathan, for the invitation. And so I will go now, and I will tell you how we are going to. We are actually in our lab trying to come up with some insights of dynamics of giant planet with global climate model. So those are the systems that we looked at. There is still the Earth, meaning that we are inspired a lot by atmospheric dynamics done on Earth. And in a way, we are basing our thoughts on principles that are true for Earth, Mars, Jupiter, Saturn, anyhow. So we look at those large objects that are purely atmospheric planets. I can start my video, actually. Can you see me? Let me check something. Yeah, just a short interruption.
We're not seeing you, just the slides.
Okay. Just a second. It should be, yeah, sorry for the interruption. So now you should be able to see me, and I will share my slide again. Okay. Yes. So, so we want to take those planets and to understand how their atmospheric dynamics works. And I like to show the following slides usually because people don't realize. So these are two planets in the infrared that you of course have recognized easily. On the left is Jupiter, on the right this is the Earth. Actually, this is the water vapor channel. But I like to show it because it is showing that if we look at the Earth in a specific wavelength, well, we can see it as a much more dynamically active planet than if we just look in the visible. And in a way, it will make it resemble much more to the kind of planets that we are interested in today, which are giant planets. So giant planets, as you know, they have large-scale jets, systems of Alton jets. And here I should point out that on Jupiter, it is very easy to see directly invisible. On Saturn, you have to work a little bit. You have to use some infrared filters to see that, but because there is a large-scale haze on Saturn. But if you use the right filter, then you would be able to see that Saturn, same as Jupiter, has those systems of large-scale Alton jets. So on Jupiter, those jets will reach a speed of about 100 to 150 meters per second. And then on Saturn, it is kind of similar, except that you have a huge, humongous equatorial jets that reach about 500 meters per second. So you see that both planets have a system of jets, but there are differences. They don't have the same number of jets, and the speed of the equatorial jet is much stronger. Obviously, there are also interesting differences, other interesting differences. Here is one, which is quite fascinating. On Saturn, so this is on the left, there is a circumpolar jet that is of almost pure hexagonal shape, while on Jupiter, and that has been revealed by the Juno mission, there is no such circumpolar jet, and there is a wealth of vortices, large-scale vortices at the pole. So there is a very strong difference between the two poles here. And if I come back to the hexagonal jet, in the middle of this hexagonal jet, close to the pole, there is a turbulent vortex at the center. There is also very active weather in those planets. So here I'm showing just a couple of examples. I'm showing on the right, you know it very well, this anticyclone large-scale system, which is done at the Great Red Spot. I'm mentioning it because in the middle of this Great Red Spot, you have a lot of convective activity, of moist convective activity. And on the right, this is actually an amateur astronomy image, along with a Cassini image. You see that there is this large white spot that correspond to a huge convective storm that has raged on Saturn in 2010 and 2011, and that has brought to the visible layer a lot of particles, and in particular water ice particles. So the weather is very active on those planets, and of course this causes some eddies and some large-scale vortices that in turn would influence the jet system. If we look at Saturn in infrared, we could also see that if you follow the banded jets, you would also see that inside those jets, you do have some disturbances and some waves that are of very high wave number. This is named a ribbon, and this is an interesting point to study with models. And then you have also small-scale waves, small-scale vortices, and you have a very, very rich dynamics on Saturn. There is also, you know, the images on Jupiter. It is even more turbulent looking than Saturn. And the Juno spacecraft that is orbiting Jupiter since 2016 has brought up a lot of those kind of images. So here you see a lot of turbulence. And we can also see the white patch that you see here are very nice high-resolution images of convective clusters and convective clusters made of water ice. And so the condensation of water is also a fuel for the atmospheric dynamics on Jupiter, as it is the case on Earth. And then on Saturn, this is also the case for Jupiter, but I will focus here on Saturn because I will talk a little bit more about Saturn. There is a stratosphere on Saturn that is created by the presence of methane and aerosol at millibar and tens of millibar levels. And what is interesting is that not only, as I talked about before, there is a rich tropospheric atmospheric dynamics on Saturn and Jupiter, but there is also a rich stratospheric dynamics. So we really have systems that have two layers of its atmosphere that are really rich in wave mean flow interaction. And it is actually interesting because the Cassini spacecraft, as you see with the colors here, with the color line, the Cassini spacecraft lasted long enough to sample half a year of Saturn weather and evolution of the atmosphere, which means that we have some sampling of the seasonal trend on Saturn. And since the obliquity of Saturn is close to the Earth, that means that when we measure at various years the meridional temperature gradient, this is what you see here, and the colors are representing the various years. So blue is the beginning of the mission and red is the end of the mission. And you see that there is a reversal of the meridional gradient, and that the baroclinicity of the atmosphere that is created by those seasonal trends is actually quite strong on Saturn. And last but not least, using thermal infrared spectrometer on board the Cassini, and also ground-based telescope monitoring, a decade ago, the colleagues were able to evidence that there is actually some equatorial oscillation on Saturn that do resemble the quasi-biennial oscillation, semi-annual oscillation, which are stratospheric oscillation that you find in Earth's stratosphere. Those kind of circulation, I should stress that those are not really waves. Those are really, like in the zonal mean sense, the atmosphere that has very strong switching between eastward jet and westward jet that are piled up in altitude in the stratosphere. And the periodicity of this, because you actually have a downward propagation of this signal, and the periodicity of this has been shown by ground-based observation to be semi-annual on Saturn. And actually, again, the Cassini mission lasted long enough to follow the evolution of this equatorial oscillation and to show that there is a downward propagation of this oscillation that appear in the zonal mean set. So basically, here I've told you in this introduction that exploring Saturn with instruments is actually quite rich, and now we are trying to make sense of that with computers. And actually, our main tool here will be numerical modeling. And this is interesting because all the phenomena that I've been showing you so far, they are actually on a large range of scales. So that goes from the smaller scale, most convective storms at small length scale and small time scale, towards the jet system, which is at a very large scale and very long time scale, because the various measurements of wind carried out on Jupiter and Saturn show that the jet structure is not varying very much, or actually very slightly with time. And so what is important, and this is what you see on this with the small green lines here, is that if you were to run a model, and here this is 1 degree latitude, longitude, half a degree latitude, longitude, etc., etc., to do some eddy resolving or at least eddy permitting simulation on those kind of planets, it is quite challenging because you have to go to fine scale resolution for your models, but you also have to resolve those large planets. So that means that you have to use some pretty computationally expensive numerical modeling. And I should point out here that I will place myself and ourselves, because I will be talking about the work from the group. We are on the right. We are using shallow model, which means that we don't have models that extend very deep downward the Jupiter and Saturn atmosphere and interior. We kind of take the weather models and we set up a boundary condition that is usually a drag to represent the fact that once the jet would go down inside the giant planet interior, they would encounter some magneto-hydrodynamic drag that would actually slow them down to zero. But we don't go down to those levels where this magneto-hydrodynamic drag is actually active. We just parameterize it at the bottom of our model, and our model here has a bottom at 3 bar or at 10 bar. But there is another kind of model that I won't be talking about today, but which has a very interesting line of research as well. Those are the deep models, where actually the weather layer is just a kind of only one level at the top of the model, and then in this kind of model, you resolve the interior convection of the giant planet. What is interesting is that in both cases, you have pros and cons, but in both cases, you are able to get the jets of Saturn and Jupiter. Okay, so our project here is to say, well, you have all those observations on Jupiter and Saturn, and let's take all those observations together and try to see if with a single model, we are able to reproduce or not the phenomena that are observed on Saturn and Jupiter. And here, we are not obsessed with trying to reproduce as much as possible what we get. We really want to run our model, to know very well our model, and to see what we are able to reproduce and what we are not able to reproduce, to see how we can understand the processes that are going on in the giant planets. So what I will be talking about today is mostly published. We have a total of 4 papers, and soon it will be 5, that discuss the various implications of our global climate modeling of Saturn. So now for about 2/3 of my remaining time, I will be talking about Saturn, and then I will turn to Jupiter, for which we have had some recent work as well. So the story starts with a kind of challenge. To build a global climate modeling on Saturn, you need 4 elements that are quite difficult. The first one is that for the seasonal trend, you need to include the relative transfer computation in the model, and that has not been done in previous models. The second one is to actually be able, as I told you before, to resolve the small-scale instabilities in the model. And then the third one is that since there are interesting things going on in Saturn, both in the troposphere and the stratosphere, we want to extend it to higher, to upper levels. And then the last one is that ideally, but this is a topic on which I have not we have not been working. Ideally, you would want to couple the weather layer of Saturn with the interior convective and magnetic fluxes. So the first step was actually for us to build a relative transfer. So that was done by my colleague Sandrine Gerlet. And basically what we want is we want to have a fast enough radiative transfer model. I won't get much into the detail. This is just to tell you that in the Saturn computation that I'm showing, we have a full seasonal radiative model, meaning that we get the influence of the absorption of gases, we get the influence of aerosols, we get the full seasonal cycle. We also include the ring shadowing, we also include an internal heat flux, and basically we are able to account for the meridional seasonal variability of the meridional gradients of temperature, but we also get correct, satisfying vertical structure of the atmosphere of Saturn, as you see in this plot here. And the way that we do it is we actually use high-resolution spectral measurement, and we put that into a simplified radiative transfer model. This uses actually the correlated K technique, and we replace all those lines with a large-scale, large bin of absorption coefficient using the correlated K technique, and that way we get a very fast and efficient, yet quite faithful radiative transfer in the model. So that was the first step. Then the second step is, now that we have a seasonal model, we want to couple it. And we want to couple it with a hydrodynamical solver that is able to resolve those small-scale interaction in Saturn. And for this, we have relied on a model that was being developed in my institute at LMD, based on an icosahedral grid that you see here. The main advantage of the icosahedral grid is that that could use the massively parallel computers that are available now with excellent scaling and without anything such as the pole problem, etc., etc. And this is actually a technique that has been used by a lot of groups worldwide. So we had that new dynamical core, that new hydrodynamical solver that was developed in our institute. So we thought that it would be a good idea to use it and to test it on giant planets. And now this dynamical core is used on Mars, Venus, and of course also on the Earth. But here, actually, one of the first application of this kind of model was for the gas giant, because we didn't need a vegetation model, we didn't need the topography model. So in a way, that was a numerical experiment that was a little bit simpler than the one that we have on Earth. So we actually refined the grid by getting a higher and higher order of discretization of the icosahedral grid. Numerically speaking, it is an advantage to use on the clusters. So I will show you a kind of experiment that we've done with this model to show you the kind of capability of this kind of model. So I will switch screen sharing so that you can see the video. Okay. Are you able to see the video? Yes?
Yes.
Okay. So what you see here is 8-degree simulation. So this was kind of a huge simulation. It was more a computer experiment than a true dynamical experiment, although it shows some very nice jets, powerful jets, some very nice vortices, and some interaction. And you will see that we will dive into the planet with the representation that we have, just to see how the fine grid that we are using. And then we will zoom out, and we have changed the variable that you see here. It is now vorticity, and you can see very well that there is a lot of eddy production. And if you look carefully to the pole, you will see a burst of eddy that is created, and that creates in turn some other eddies, and that organize as large-scale eddies. So there, it was more computer experiment. It was because there was actually an interruption of the main cluster. And just after the interruption, since they were testing the cluster, they told us, well, are you interested to use the whole cluster? And then we were able to run that simulation. So that is a simulation that is very expensive, very nice. But unfortunately, we were not able to use it really on Saturn, because we also needed to use some radiative transfer computation, etc., etc. So we needed to set up a kind of trade-off, and we ended up setting the horizontal resolution to 1/2 degree at the time to be able to run on Saturn. So let me share again the, sorry. Okay. Because the main problem is that on Saturn, of course, 1 year of Saturn is 30 years of Earth. And since you need some spin-up time on Saturn, that is quite large, that means that the simulation has to be quite long. So here is the model that we got. So we joined together the two parts that I've been talking to you about, the dynamical core and the radiative transfer that we compute in on each grid point, and then we have this model for giant planets. So there are a couple of details in this slide. This is more for kind of reference, but we've used horizontal resolution of 1/2 degree. We start from a no wind case, and we start with a temperature profile that is uniform over the whole planet, and then the radiative transfer is computing realistically the meridional gradient that you get on Saturn. So the first thing was to check with observation that we do get the right seasonal evolution. What you see here is temperature at two relevant levels. And what we wanted to check here is that the meridional, the latitudinal gradients of temperature and also the temporal phasing of the season was good in the model. The lines are from the model, and the crosses and squares are from the observation coming from Cassini CIRS. And you see that the amplitude of the meridional gradient of temperature is really correctly represented in our model. Of course, we depart from observation close to the equator in the middle stratosphere, but it is because we have those equatorial oscillation, and I will come back on that topic later. Also, we are able to map vertically and again meridionally the temperature field, and you can see that the model is reproducing a thermal structure of the Saturn atmosphere that is quite satisfying. And again, here I should point out how essential the Cassini spacecraft was into allowing to constrain our model. Last thing is that we can also look at the temperature gradient, the meridional gradient, close to the bottom of the model in the troposphere. This is quite important for the baroclinicity of the atmosphere. And here we can see that we have about 4K gradient between equator and the pole. And in the observation, this equator to pole contrast is half what it is here, which means that we know from the beginning, from our model, that we have an atmosphere at the bottom that is more baroclinic than what you would expect on Saturn. And this is something that we have to keep in mind. Okay, so now here is the jet structure that we get from our model. Superimposed the lines are the temperature field that I was just showing. And what you can see here, so this is altitude or pressure level and latitude. What you see here is that we do have in red eastward jets in our model. We do have some amount of baroclinicity in the atmosphere, especially in the stratosphere. And you can also see that close to the equator, we do have a super-rotating jet. But the main observation of that is that even using a long equilibration time of our model, we get only a weakly super-rotating jet, which is 40 meters per second, to be compared with the 400 meters per second that is observed on Saturn. So here, clearly, this is the first thing that we learned from the model is that for the equatorial superrotation, we have to add something. And I will come back later to that point with the Jupiter case. So here are some maps. You have donal velocity on the left and potential vorticity on the right. So you see the jet structure, and you also see that in our model, we do get some eddies, we do get some waves, we do get some large-scale vortices. So you see that compared to the 1/8 of a degree case that we saw before, 1/2 of a degree has some quite dynamic atmosphere and at least gives some reasonable features that are observed on Saturn. So first, here I won't comment this, but this is just to say that we are able to explain the super-rotating jet by looking at the forcing term and the main forcing term from the Eliason-Pan flux, and we are able to show that this super-rotating jet is coming from the activity of Rossby wave in the tropical atmosphere of Saturn. About the vortices, I won't elaborate a lot because this is a work in progress. We have worked on a lot of points to interpret our simulation here, but the large-scale vortices is still a work in progress. So I'm just giving a heads up here. We have Patrick Donnelly that is working on that, and we are working out some statistics of those vortices, looking at cyclones and anticyclone, looking at the lifetime of those large-scale vortices. And this is something that we are preparing. This is a work in progress that we need to do in the incoming year. So that being said, now let's talk about the eddies. And here I'm showing, in lieu of zonal velocity, I'm showing the meridional velocity. And you see that the wave activity and the eddy activity is very rich. And you can see that close to the 30-degree latitude. So that will be around 30 degrees here. So you don't see my mouse, but this is a wave that is located at the very strong potential vorticity gradient that you see at the 30-degree latitude. This wave, we were able to show by some analysis that this was a wave that was a wave number 19, that this was a Rossby wave, and we were also able to compute its period. And what is really nice is that this kind of wave was actually observed by Cassini as a ribbon wave. What is interesting is that Cassini was able to observe a lot of zonal planetary wave number from about 10 to 20 to even 80, and what we see here in our model is a reproduction of the wave that has one of the lower wave number observed by Cassini. Then we also have other features, which are those jets. And what is interesting is to have a look at the evolution of those jets in the full duration of this simulation. We have done a simulation for 15 years of Saturn, and here is what we get. So this is basically the jet system. So this is zonal wind speed with respect to latitude and a simulated Saturn year. And what you see is that it takes about 6 to 7 years for this jet system to equilibrate. And then before there is a migration of jets, and that might actually be related to the quite strong baroclinicity that we have in the atmosphere. But in the end, we have some stabilization of the jets at some latitudes here. Interestingly, there is still some evolution, still some slight migration of the jets. And if we were, but that is too expensive, but if we were to prolongate the simulation, we would see a slight drift of those jets. What we see that is interesting is the fact that with this jet system, if we look at the eddy kinetic energy, we can see that the eddy kinetic energy maximum is basically not continuous. So there are some eddy bursts that you can actually see also in this evolution of jet. You can see that there is some sudden acceleration. This is due to some eddy bursts, and actually the strong eddy activity that you see in this image here in the mid latitudes correspond to one of those eddy bursts. And one of the questions that has been studied a lot in the journal Planet Science is how those eddies are able to maintain the Alton jet on Saturn and also on Jupiter. But before I turn to that topic, I would like to comment on what is the origin of those eddies. For doing that, we have, so I'm sorry for the busy plot, but this is just to say that this is something that can be found in any good textbook of atmospheric dynamics. But basically speaking, you have some necessary condition for barotropic and baroclinic instability. And we have analyzed in our simulation this kind of criterion here. And what you have to keep in mind basically is that whenever there is a change of sign, that would mean, for instance, for barotropic instability, that barotropic instability is possible. This is just a necessary condition. And you see here, for the same jet structure, but with a criterion for barotropic instability. We see that those mid-latitude jets are reasonably barotropically unstable in our simulations. And actually, this could be expected because since we get the ribbon waves that has been argued in some idealized modeling that they could be related to barotropic instability, it is not a surprise here to find that the eddies that we have here could be due to barotropic instability. But in a nutshell, we were also able to find that looking at the vertical shear of the zonal velocity and also the potential vorticity gradient, we were also able to pinpoint that baroclinic instability is also occurring in our simulation. So in our simulation, we have both barotropic and baroclinic instability. Now the question is, when you have such eddies with barotropic and baroclinic instability, do they actually accelerate the flow or do they slow down the flow? And for that, I'm going to turn, without going into much detail, just to give you a view of a different point of view that we can take with models. The first one is the global view. The global view is to say, well, let's look at a global scale mean, an annual mean of the quantity C here, which is U prime V prime multiplied by the jet curvature. If that is positive, this is an indicator that there is transfer from the eddies to the zonal wind. What is interesting with this diagnostic is that this has been measured on Saturn by Del Genio and Barbara. And so we can compare the values. What is interesting here is that we do get an order of magnitude that is the right one, but we do get quantitatively something that is half the value of what is measured by Cassini, which means that in our simulation, we have a good amount of eddies and their energy is the right order of magnitude, but maybe we miss a source of eddy and we miss a source of forcing of the jet, and they could be stronger than what our model is showing here. So that might be an explanation for the very slow superrotation that we get. And we can also turn to local view. And in a way, I have already talked on that topic because, well, the local view is simply to say, if you take a given jet, it may be accelerating because there is some eddy forcing. And supposedly, if those jets are maintained by some eddy activity, we should have an equilibrium between the term in green, which is the residual mean term, and the term in red, which is the eddy term, the eddy forcing term that corresponds to the divergence of the Elias-Pan flux. And this is what you get in the first plot. And you see that this equilibrium is respected in a model. But there are slight modifications of this equilibrium. And there is a little bit of imbalance. And this is what is causing either the jet acceleration or the jet migration. And you see in the bottom plot that from left to right, you have jet acceleration, a jet that is not changing, and then the jet that is migrating because of the action of those eddies. Then we can also take a step back and try and look at a harmonic view of the flow. So this has been done, so this is some work and papers that has been done by a postdoctoral fellow that was in a group, Simon Cabane. And basically what he said is that he took the GCM result and he explored if the dynamical regime that is followed by our model is compliant with the observation. And supposedly in a giant planet, we should be seeing an inverse cascade, and we should have transfer from the small scale eddies to the large scale eddies with a peak that is close to the Rhine scale where the energy would be accumulating. And in addition to that, so in addition to that reverse cascade, we should have a zonostrophic regime, meaning that the rotation of the planet is able to channel some additional energy. And in that case, that means that basically you would have a slope of the spectra of energy that would be to the power of -5. This is what we get from our model. So the red line is actually the zonal flow, and we are able to evidence the zonostrophic regime here. We also have the eddies that are following an expected slope of -5/3. And what is interesting is that in the zonal energy spectra, so for the mean flow, there is a peak of energy close to the Rhine scale that does correspond to the scale of the jets. So basically, what Simon Cabane was able to show is that our modeling supports what is found by observations. Now, we have done some additional thing because when you have a model, of course, you can do some tests. So our reference simulation for Saturn, it was kind of like we were looking at specifically forcing the seasonal cycle of Saturn, but we took a step aside with Simon, and what we did is that we forced the flow. So we switch off the radiative transfer, and we forced the flow with some Taylor-Green vortices. So this is a simple forcing that is very convenient because you can set up the scale at which you are forcing. And then because of the rotation of the planet, then you get some jets that are akin to the ones that we get in a reference simulation. But since this is idealized here, we were able with Simon to try various rotation rates. And by trying various rotation rates, we were able to show So I'm sorry, this is a busy plot, but the takeaway message of this chart here is that as long as you slow down the planet with the same forcing, you get actually a reverse energy cascade that is less efficient than what you get with a fast rotating planet. So in our case, this is quite important because we have a shallow model. So here, what is really doing the reverse cascade is not the shallow dimension of our model. It is really the fact that we are fast rotating, and it is believed that Saturn behaves this way in reality. Okay, so last point about Saturn. How much do I have left, Jonathan? 10 minutes?
Yeah, so you could go, you got 10 minutes left, Aymeric.
Okay, great. Yes. So within those 10 minutes, I will talk to you about Saturn stratosphere in our model, and I will talk briefly about our Jupiter simulation. So basically, this is a list of challenges that we have. So we set up the model to fulfill number 1 and number 2. And now what about number 3? Number 3, which is that we wanted to extend our model to the stratosphere to look at stratospheric dynamics, especially the very nice equatorial oscillation that was discovered by Cassini. So what we know from the Earth's atmospheric science is that to get some equatorial oscillation, you need large-scale wave, you need planetary wave at the equator, like Rossby wave, Kelvin wave, and inertial gravity wave. And in the reference simulation, we were able to find a whole spectrum of waves that you see a hint here. If you look, so this is the same chart that I showed before. If you look close to the equator, you would see that there is a low wave number mode here, which hints at the fact that we may have a rich atmospheric dynamic at the equator of our model. So what we did is that we carried out a specific wave analysis at the equator. So basically, this is the Fourier transform that you see here. This is frequency as a y-axis, and then wave number, spatial wave number as an x-axis. This is Wheeler and Kiladis spectral plots. What is coming from the model is actually the black points here. And the lines that you see are the dispersion relationship that you expect. So on the left of the left-hand plot, you see the Rossby waves. On the right, you see the Kelvin waves that are eastward propagating. And then on the right, you see Rossby gravity waves. So you have a wealth of those planetary waves that we know on Earth are involved into the equatorial oscillation. So the main question now is, are we able to reproduce with our model the stratospheric oscillation? The main problem that we have is that in the reference simulation that I showed you, we didn't go high enough. So we had to do some specific work to extend the model top, and all this stratospheric work that I'm showing here has been done by former PhD student Deborah Bardet. So once you extend the model top, as you see here, you start to have some very nice equatorial oscillation at the equator that are the result of those wave forces. And the first study that we did was with a low resolution in the stratosphere. And what we were able to show, so again, here, this is latitude as a y-axis and the time in Saturnia as an x-axis. And what you see here is that we do see some periodicity close to the equator, but the periodicity is not very clear. We were looking for, as I recall, half a year periodicity, as is shown in the observation, but it's not entirely clear when you look at the equatorial location in the top plot. Now, in the bottom plot, you can also see that the downward propagation is quite irregular. So that was a preliminary work, which was very promising because we were really feeling like we could reproduce this equatorial oscillation since we resolved those planetary waves. And then what Deborah Bardet did is that she ran another simulation, quite computationally expensive, where she refined the vertical resolution in the stratosphere. And what we got was very rich. We got a reference simulation that has very rich stratospheric dynamics. And in particular, using that high vertical resolution, we were able to get a much more periodic oscillation that was really having the same characteristics as the observed one, and that has a very nice semi-annual periodicity. And when we had a closer look to the forcing in a simulation, the stratospheric dynamics of it, we came across, and Deborah Bardet discovered that there is also some inter-hemispheric transport that bears much resemblance to the Brouwer-Dobson circulation on Earth. And that was very exciting to us because it was shown by hydrocarbon measurement on Saturn. It was shown that actually there was a large-scale transport in the stratosphere that was not explained by previous models, and that kind of circulation is able to explain it. So, of course, I won't show you the whole analysis, but this is summarized in this plot here. And what is interesting is that actually the stratosphere of Saturn looks like something very similar to Earth. You have some equatorial oscillation. So here, this is the solstitial circulation on the stratosphere of Saturn. And you have a combination and a joint evolution of both the equatorial oscillation and the interhemispheric Brouwer-Dobson-like circulation on Saturn. And what is interesting is that there is a synchronization. So for instance, the westward face is of the stratospheric oscillation, of the semi-annual oscillation, is synchronized with the Brouwer-Dobson circulation. In addition to that, the Brouwer-Dobson circulation is associated with a Rossby wave surf zone, kind of like what you get on Earth. What does that mean? That means that here you have a very strong forcing of Rossby wave that force the interhemispheric oscillation to strongly deviate in a downward direction. And what is interesting is that in that location that you see here, in the soft wave and in the location that you see in gray, this is where the ring shadowing is present at this season. And the observation from Cassini were showing that at this season, in this location, the atmosphere was much warmer than what the radiative transfer model were indicated, like much, much warmer, and that couldn't be explained by radiative transfer. What we argue here is that this is dynamically driven, and this corresponds to the descending branch of this interhemispheric circulation that adiabatically warm the atmosphere of Saturn. Okay, so in the last couple of minutes, I will turn to Jupiter simulation. This is very easy to explain because basically we have applied the same methodology and the same approach to Jupiter. And one point of interest for us on Jupiter was that super-rotating jet. Because when we run, I will skip that because we have designed the physics quite similarly at what we have done on Saturn. What is interesting is that with the same model, we run a simulation for Jupiter and Saturn. And if you look at the equator, you would see that Saturn is weakly super-rotating, while Jupiter is not super-rotating at all, which is really at odds with what is observed. So we thought this is a specific topic that would be worth being investigated. And that has been done by Alexandre Boissino, who was a PhD student in the team. And our idea was to use that pathological Jupiter case at the equator to test the effect of the parametrization for moist convection in Jupiter. So I won't get you into all the details of this parametrization, but it is a way to represent sub-grid scale moist convection and the forcing it had on the momentum and the heat mixing in the atmosphere. And what we were able to find is that we were able to make this super rotation appear in our simulation with a very reasonable a value of 100 meters per second compared to the observation on Jupiter, if we assume 3 solar abundances of water vapor in the deep atmosphere of Jupiter. And this actually is close to the value that is measured by Juno recently. So our argument is that to get a correct superrotation in our models, we need to account really in a very serious and thorough way of we must account for moist convection. And this is something that we are going to try now on Saturn. Now we skip the last slide to allow some time for question, and I will summarize here. So basically, we are using global climate modeling with the full radiative transfer for giant planet. We see a lot of interesting waves and jets, and we are able to formulate that eddies are driving the jet in some different point of view. This is allowed by the model. The stratospheric dynamics is really very insightful in the model. We do get semi-annual oscillation, and this is actually how we interpret it from the model. So this is not really looking like a QBO. This is really forced like a semi-annual oscillation, and you also get a Brouwer-Dobson circulation. And as I just showed you in our Jupiter model, by accounting for moist convection, we were able to get an equatorial superrotation in the model. And a future project in the team, there are some ongoing projects to now apply that to ice giant because, well, there will be flagship mission from NASA in the far future. And we are also interested into trying to represent convection not by sub-grid-scale parametrization, but by resolving the convection with cloud resolving model. So thank you very much for your attention. And now I'm happy to answer to questions if there are any.
Great. Thanks so much, Aymeric. That was just so much fun. Let's hear some questions. Well, while we're waiting, I'll ask one. So one of the really cool things I noticed. Oh, actually, we have Dennis asking. Yeah, go ahead, Dennis.
I mean, that's okay. You can start talking, and I'll take it from.
Oh, feel free. You go first.
Okay, thanks. So thanks, Aymeric. That's a brilliant talk. Regarding the cloud resolving model in the future and your simulations of Saturn and Jupiter, what is the appropriate horizontal resolution for your model to represent convection correctly for these giant planets? Because we know for Earth, for example, that to get a convective permitting simulation, we need to go down to maybe a few kilometer grid scale. What is the resolution appropriate for Jupiter or Saturn?
So yes, so thank you very much for this question, Dennis. When you start a cloud resolving model study, well, actually, this is one of the answers to the study to know the resolution that you would use. But I would say that for giant planet, we can first focus on the large scale storms, and I would say that going to the kilometer is a bit overkill. I'm assuming that we could get good results with, let's say, with 10 kilometer resolution, because actually, for instance, the plume that has been incoming from the depths of Saturn in the case of the Great White Spot is quite large, actually. It is actually of the size of the Earth, if you wish. So we could really use, the main point is to be able to get a good vertical to horizontal ratio to resolve the strong vertical motion. So I'm assuming we can go and we can start with 10 kilometers.
Okay, yeah, great, thank you.
And one of the interests of that is to actually be able to resolve the stratosphere, because the great white spot on Saturn has implied a very strong warming of the stratosphere. And so everyone knows very well that on Earth, when you have strong wave activity, then you can get sudden stratospheric warming. So on Earth, this is caused by the Rossby wave breaking. But in the case of the Saturn storm, that might be something that is a forcing of the gravity waves that are then propagating upwards and then breaking and warming the atmosphere. And this is something that has been discussed just a little bit as a possibility in the papers, and using cloud resolving model will be interesting for that, because we will resolve both the convection and the created gravity waves.
Yeah, presumably your results about QBO-like oscillations would be particularly sensitive to moist convection, right?
Yes, actually, that is there is another question, and a very good question, because there has been an observational study in I don't remember. I think this is a Lee Fletcher paper. That is for sure, and that is in 2018. And this paper has shown that the great white spot had somehow disturbed the signal of the equatorial oscillation. So indeed, we would also try in a model to put a disturbance like the great white spot, and to see how the equatorial oscillation that we were able to reproduce could be modified by this event. Yes.
Cool, thank you.
James, did you have a question to ask? Nothing right now? All right. So, you know, let's do the following then. We're just about out of time. And normally we stick around and ask questions informally. So why don't we go ahead and do that now? We'll say thanks a lot to Aymeric for the wonderful talk. And if anybody wants to stick around and keep talking, we'll do so informally, but we'll go ahead and end the recording now, and see you guys in a couple of weeks.